Morning, everyone, including Ton. Welcome to the last seminar this calendar year. So we are not going to have seminar next week. It's a research departmental research day. So it's Linus is closing our series for this calendar year, not the academic year, but calendar year. Yeah, it's Linus. Linus comes originally from Germany, University of Bochum, where he did his bachelor and master studies, and currently he is a joint PhD between KU Leuven and Edinburgh. And today Linus is going to talk about his PhD research. I believe Linus still has like a year to go in his PhD. And research concerns the study of exoplanets, in particular atmospheric characterization, where Linus uses transmission spectroscopy as a tool for these studies. Okay, so the floor is yours, Linus.
Yeah, okay. Thank you for the introduction, Andrew. So I'm going to talk about atmospheric characterization of exoplanets and then focusing on transmission spectroscopy. So I will talk about all the basics, how it works. And then I will switch to one example case. So here we have an overview of the talk. So as I said, first an introduction, and then I will talk about HET B12b, which is a warm sub-Saturn, Saturn-sized planet. And there I worked on data reduction and also on some retrievals. And I will talk about how that works and what kind of first results we got from that, or what kind of results we got from that. Yeah, so starting with atmospheric characterization in the era of JWST, because it changed a lot. So here we have a very traditional way to start an exoplanet talk by showing a plot of the demographics of exoplanets. So here I plotted mass versus radius. Another common way is to plot distance or orbital period against radius, and we can see all these kinds of interesting blobs where we have different types of exoplanets. But this is mainly here to show we have a lot of exoplanets, a lot of different types of exoplanets, and so we have, according to the NASA Exoplanet Archive, so different archives give slightly different numbers, we have 5,788 exoplanets discovered so far, which is quite a lot. Actually so many that nowadays people mostly just say we have over 5,000 exoplanets, soon over 6,000 exoplanets. So we are very much out of the era of just finding them, collecting stems. We just have now large populations, try to study them. And another thing that is interesting is to try to learn more about them. So if we just have information about mass and radius, which we get from the common detection techniques, we can already make some assumptions about the interior structure, but a lot of that is very degenerate, so it's interesting to learn even more. And one way to learn more about them is to study their atmospheres. And so here now I've marked in red planets for which we have some kind of atmospheric characterization. So for some of them, they're not really characterized in detail. But the exoatmospheres database identifies 249 planets that have been characterized so far. So we're already starting to begin to be in an era of large-scale atmospheric characterization as well, I would say. And then how to characterize exoplanet atmospheres. So the naive idea would be, of course, to just observe them directly, then take a spectrum of them, and then you have information about their emission, and then you can learn stuff about their atmospheres. But we can see already from this animation here, the kind of planets that we can directly observe, they're typically quite far away. And then if we look at a diagram where we show how we detected these kind of exoplanets, the one that we find by directly imaging them are planets that are quite large and also quite far away from their host stars, because it's difficult to disentangle the signal from star and planet. And so most of the planets we find, we cannot currently directly image them. And there are, of course, people working on pushing these limits further and further to smaller planets at smaller separations. But if we want to study the atmospheres of these kind of planets, we have to switch to indirect techniques. And these indirect techniques, they study in different ways. Basically, just the light from the star, but it's not just the light from the star, it will be the light from the star and potential planets. And then you can try to disentangle the planetary signal from this combined signal. And I think Jana showed this exact plot a couple of weeks ago. But we see different phases over the orbit. That's when we talk about phase curves, which works well, of course, for hot and large planets. But then we have also these two special events where the planet disappears behind the star, the secondary eclipse, where we do emission spectroscopy, and this moment where it is in front of the planet, and it blocks some of the starlight, which is when it's in transit. And we can learn a lot from these transits. And the fact, I mean, I showed this diagram before, a lot of these planets we discover with transits. So we have a lot of planets which are on the right kind of orbital alignment to do these kind of techniques here. Yeah, then to talk about transmission spectroscopy. So that basically uses the same, it does the same thing that a detection of a transit would do. But we use the fact that if there is an atmosphere, the amount of light blocked is not the same at each wavelength. So if we have an atmosphere, it will become optically thick at different pressures for different wavelengths. And the reason for that is that we can have molecules that make the atmosphere optically thick at a higher apparent radius, or we can have other effects like clouds and stuff like that. And then we get these transmission spectra, and then we try to fit them with models to figure out what they tell us about the atmospheric properties. Then how can we do this? One way would be, of course, from the ground, but I'm sure as all of you are very well aware, if we want to look at molecules, we want to look in the infrared, and the infrared is not really well accessible from the ground because there's an entire atmosphere in between. But we can do standard transmission spectroscopy from the ground in the visual range and like up to the beginning of the infrared. And there we can learn stuff from that already. So we have these, if we have cloud and haze particles, we see these slopes, these Rayleigh scattering slopes, which we can characterize to find out information about the properties of cloud particles. And then we can see some atomic features and maybe even some molecular features. But most of the stuff that we're interested in will be further into the infrared, and that's not accessible from the ground. And then just for completeness, there's another technique called high-resolution cross-correlation spectroscopy, so that we don't get transmission spectra, but we cross-correlate spectral templates. Test? Okay. I hope this is better. Where we cross-correlate these spectral templates, and then what we can do with that is that we can detect molecules. And the main thing we can do with that is just detect, because we don't get these transmission spectra over a wider range. It's harder to obtain these constraints on abundances. So yeah, good for detection, not so good for understanding how much of a certain molecule is in an atmosphere. Yes. Okay. And if we want to do this thing in the infrared, we have to switch to space. And so here I have a plot of the data we had for the planet that I will talk about, HET-P12b, before we had JWST. So we have data from HST here. We can see a bit this slope in the visual. We can see one spectral feature here with the wide field camera spectrograph, where we see this one bump that has been attributed to water. And then we have these photometric Spitzer data points where you might say, oh, maybe it goes up, so maybe there's a spectral feature. But that's, of course, all very difficult just with this data. And so now if we include JWST, the picture is completely different, right? So we have these, we have this much better spectral resolution, this much better coverage up to 12 microns. And we can see all these kind of features here that we try to characterize. So that really changed a lot. So then to highlight some results that we found with JWST, so one of the first things that was found within one of the early release science programs was spectral features from sulfur dioxide, both here and another one further in the MIRI range. And so that's interesting because you wouldn't necessarily expect that just from equilibrium chemistry and mixing this kind of stuff. But it's evidence of photochemistry, and here's a diagram how that works. So you basically split water molecules, and then you have radicals and a chain of reaction. In the end, you form sulfur dioxide. And you need this constant process of pushing the chemistry out of equilibrium to produce sulfur dioxide. So that was one of the new things. And then another thing that was found in several cases, I think, but also in one study that was led by Lehn, so many people from this institute involved, was the detection of silicate cloud features. So clouds are a thing we've always seen in exoplanet transmission spectra, but often they just reduce the strength of our features, so they're a bit of a nuisance. But now in the MIRI range, we can also see these characteristic bumps, which can be attributed to certain types of silicates. So we can learn something about the composition of the cloud particles as well. Then switching to the case study on HET-P12b. So first a bit about what is HET-P12b. So het B12b is, I listed some of the properties here. So it has a radius almost of Jupiter, but its mass is quite a bit lower. So it's a bit of a puffy planet. It's on a short-ish period. And it orbits a K-type star. I also included these names. They have nice names from the IAU that unfortunately nobody uses in astronomy. So it's called Pooley and the star's called Commando, but everybody will just say het B12b. And then it's interesting to compare to the planet that I showed before on this transmission spectrum, WSP 107b, because they're quite similar in many respects. They have similar host stars. They have similar radii, but WSP 107b is even more inflated. So it's interesting to see how these planets compare, and then we can do already this kind of population studies where we try to understand why do we see this certain spectral signature with one planet and not the other planet, where we need more complex modeling for. Then I already said we have these previous observations, and people, of course, try to characterize the atmosphere based on that. So we have the slope, which shows up more or less in some of the reductions, so there's some controversy about that. But people use that to characterize clouds, and then also we see here like the lower limit to the transmission spectrum. People also use that to get constraints on the position of clouds in the atmosphere. We got information about the water content, and this can be fitted with a CO2 feature. But of course, with the JWST data, now we can get much better constraints. And then we have these new JWST observations. So we have 3 transit spectra with 3 different instruments. This data was taken as part of the MIRI European Consortium, GTO program 1281. I listed some of the collaborators. Also some people from KU Leuven, of course. Thomas is in the audience. And this is all part of this ExoMIRI subgroup that we have there. So we have NIRSpec, MIRI LRS, and NIRISS SOSS, and all of these result in different papers with different focus. So this paper should appear soon, I hope, right? It went through an extensive review process, and it focuses on these kind of features that we can see in the NIRSpec range. And then the MIRI paper will focus about, do we see evidence for SO2 or not, and silicate clouds. And then this NIRSS SOSS paper, I try to combine all these data sets to see what we can learn from the different instruments and how they affect the kind of constraints that we can get. So how does this work? We start with these, I will go a bit through the whole process. So we start with these raw images from JWST, then we do data reduction to turn it in the end into a transmission spectra, and then we do these atmospheric retrievals where we get these posteriors with constraints on the different parameters. Talking about data reduction. This is, as I said, I worked on the NIRSS SOSS data, which is the one that covers the shortest wavelength range from 0.6 to 2.8 microns. It's a bit more complicated than other JWST instruments due to overlapping traces. So we have these multiple spectral orders. We interested mainly in the first one, which is the strongest one. And then the second one is also interesting because we can extend to the shortest wavelengths to 0.6 micron. And then it's also slitless, so we can have contamination from other sources, which is something that sometimes is harder to deal with. And then how did I do the data reduction? So I used the ExoTetraF pipeline, which is one of the publicly available pipelines. There are several, but this one is specifically made for NIRSS SOSS reductions and takes some of the peculiarities of that data into account. And many of these pipelines that we use, they basically in the background use a standard JWST reduction pipeline, and then they apply some additional tweaks for transmission spectroscopy, leave out some steps, provide some alternatives that might improve the results. And then we get the spectra of the star, so a time series of spectra, and then we still have to fit that to obtain the indirect data product of a transmission spectrum, and for that I use Juliet. I will go a bit through how that works in the different stages. So in the first stage, we apply some corrections, and then we do what is called RAM fitting. So these are all standard steps. What is a bit different, what also many other reduction pipelines or approaches with NIRSS SOSS transmission spectra don't do, is that it already corrects for a specific type of noise, the 1/f noise at this level, not just on this at the second level. And that can matter. So we start with these uncorrected images, we clean up stuff. Here the super bias is still in there, then it gets removed. We can see we have still all these kind of contaminations that might be from cosmic rays, and we have the background in there. And then here we extract this 1/f noise that we then remove from the different group images. And then I talked about that. I'm sure people have showed this plot many times before. One of the things that is new about JWST is that we have these multiple readouts before we clear the detector, basically. So we have these multiple groups, and that can be useful to detect cosmic rays because they cause jumps on non-linearity effect when we get closer to saturation, where it doesn't increase linearly anymore and just turns slightly off. And we can correct for all kind of stuff with that. That's why that's useful. And then the second stage, we apply again some additional corrections like flat field. We finally remove the background. And we also prepare for the third stage where we extract the actual spectra. So yeah, we find out where the position of the centers of the different spectral traces are. So yeah, we can see here we have still the background, then remove the background, then we end up with this cleanish image. We can see we still have some 0th order contaminations in here that could be a problem. Yeah, then we find the centers of these positions, and then we're basically ready to extract the spectra. And so this is basically the only thing that happens here. There's some helper steps that don't matter that much. And then the extraction you do, you know where the center of your traces are. Then you can do box extraction where you just have an aperture around that. And you just sum all the flux within that aperture. Or you have another thing, the Atoka algorithm, which tries to model the cross combination from the different spectral traces because they can extend quite wide, and we care about weak signals. So it can be useful to model that, but people usually stick with box extraction. Yeah, and then we get this. So we have these stellar spectra, and then if we look at the different wavelength points and see how they change over time, we get this. So these would be all the spectral light curves. We can see clearly the signal of the transit here, both in the first and the second order. In the second order, we can see it gets a bit noisier at the longer wavelengths, so people typically just go to like 0.85 microns or something and 0.6 and ignore this region where we also get data from the first order. And then we can also combine them into white light curves where we basically add up all these different spectral light curves. And that's then useful for the fourth stage, which would be light curve fitting, where we try to fit this data because we were not really interested in these light curves. We're interested in the transit depth because the transit depth and how it changes over wavelengths, that's what gives us the transmission spectrum. So we typically do this in a two-stage process. So we first create these white light curves, we fit them, and there we leave stuff like orbital parameters free and allow the code to optimize for that. And then in the second stage, we fit different spectral bins. Often we don't do this at like the full resolution of the instrument because then we get a very noisy transmission spectrum. We have to do more fits, it takes more time. So we typically already bin like slices of pixels here into smaller binned spectral light curves, fit those, and then we get all these different transit depths from that, and that then creates in the end our transmission spectrum. So here I have the transmission spectrum that I get, also comparing it to a different reduction. And I also overplotted the HST data, so now we can see we have a much wider wavelength coverage. But like in the region where they overlap, we have a very nice agreement with the previous HST data. We just now see way more features, way more water features in the new transmission spectrum. And then I also spent quite a lot of time trying to optimize for that and see, because you can do all these kind of changes during the reduction, you can tweak parameters, and what people often do is they have multiple pipelines where people follow different approaches, and then they give different transit spectra, and then they say, oh, they're roughly, they're relatively similar, so it seems like we get a good result and it's trustworthy. But we are interested in subtle changes, and they can affect what we get in the retrievals, so it's interesting to see what actually changes what. And so I tried like a bunch of different parameters to see which one make a difference. A lot of them don't really make such a big difference, some a bit bigger. And one that I picked out here is how you correct for this 1/f noise. If you only do it in the first, or if you do it in the first and second stage, that seems to have an effect where we can see here there are differences here, and they don't look so large, but they're not just offsets, which wouldn't be a big change, but we have these systematic differences. So like this feature at the end is going to much higher transit depths or less, or not much higher, but there's a difference, and we try to fit that, and then we also have this data towards the right in the NIRSpec range, and the question is like, how big is this feature? How can we get them to match up? And the same here, like, is there like the beginning of a Rayleigh slope or not? Or is this relatively flat? So we have these differences that are dependent on wavelengths, and they can affect our retrieval results. Then talking about retrievals. So what are retrievals? So retrievals basically consist of two parts. So we have some kind of forward model, and we have, of course, our data that we want to fit. And so this forward model, which is typically quite simple, we run that a bunch of times compared to the data. And then we have some kind of sampling algorithm that tries to optimize and find the best values. So that's something MCMC-like. Now people mostly use nested sampling. And so in the end, if we do that, we don't just get a best fit value, we get these posteriors of the different parameters. So we have an idea how tight our constraints are on the different atmospheric properties. And one nice side effect is we also get these Bayesian evidences, which we then can use to compare different models and stuff like that. So that's basically how that works. So as I said, we typically do some simplifications for these retrievals. So if you want to think about all the complexity involved in an atmosphere, it can be quite complex, right? So there are three-dimensional things with like all kinds of mixing and processes transporting chemicals around. We can have complex TP profiles where especially like something like clouds can lead to inversions where like, you know, it doesn't just decrease in temperature the higher up you go, and you can have like changes where the temperature increases in certain pressure levels. Then you can have all kinds of disequilibrium chemistry effect, you can have mixing, you can have photochemistry that I mentioned before, and then you also have clouds, which of course affect the spectrum by making it optically thick at certain pressure levels, but they also interact with chemistry and all kinds of stuff. But when we do the retrievals, we typically use quite simple models, so they're just one-dimensional. Often we assume just a constant temperature for all pressures, constant chemical abundances, and we have like a very simple parametric cloud model. So there are, of course, limitations that come from that. And then, yeah, the retrieval setup that I used the ARCUS code by Michiel Min, and then I used such a very limited setup, so constant temperatures, constant chemical abundance, just a simple gray cloud deck, which is basically just a limiting flat line. And then I tested how the constraints change when we combine this NIRISS data with the NIRSpec and MIRI data set. Oh, and so these are this is the result that you get out of that. So we can see we get different constraints from the different instrument combinations. Some stuff is fairly easy to understand, right? So CO2 and CO, they only have strong features in the NIRSpec range, so we need the NIRSpec data to get these peaks, to get these significant detections of these molecules and constrain them, and not just get like an upper limit that we get from the other instruments. Then all these other molecules down here, we don't necessarily have a significant detection for them. So we don't have significant detection of SO2 and H2S. With some combinations, it seems like there's a bit of a peak, but we can see this long tail, so that's probably not significant. There seems to be no methane, and where we put this limit depends a bit on which instruments we include. So for example, including NIRISS can be useful because in the NIRISS range we can have strong water features, but we can also have strong methane. Or we also have strong methane features, but we don't see any of that. But we also have methane features in the NIRSpec range, so that already told us there's likely no methane. Yeah, and then interesting about water, what I hoped is that if you include NIRISS, you would get the best, tightest constraints, but it seems like NIRISS, NIRSpec plus MIRI is almost as good as NIRISS and NIRSpec, and some of these combinations, these other combinations seem to obtain tighter constraints, which of course, you know, we have more information if we include NIRISS, so we should trust that more. So that kind of shows that some of these retrievals can be apparently slightly overconfident, right? So this would say it's higher and we have this narrow posterior, but actually if we include all the data, it gets a bit wider again. So yeah. Yeah, then of course we also fit for other parameters. So I didn't show the full posteriors here because they're huge plots. But we get similar radii. We also get similar temperatures, which are typically quite cold, colder than equilibrium temperature. And then for the clouds, there also appear similar pressure levels. It seems that the NIRSpec and MIRI retrieval converge to a different solution where it puts the cloud at deeper into the atmosphere. It's maybe something to investigate a bit more because that sticks out quite a bit. And then it's also interesting what we want to derive from these molecular abundances is where we look at element ratios and where we look at proxies for metallicity and C/O ratio. Because that is interesting for further deductions that we can make based on that. So we don't get good constraints on the sulfur abundance because we don't have strong detections for sulfur molecules. But we seem to get a C/O which is subsolar and probably also substellar, and they all go in a similar direction. But then again, there are also limitations from doing retrievals and not running like full models that take into account all these disequilibrium effects and stuff like that. So Thomas worked a bit on that for the NIRSpec data, and then we can get quite different results if we use like more complex forward models. Then looking at the best fit model for when we include all the instruments, we can see we fit quite nicely all these water features here or most of them quite nicely in the NIRISS range. Then we have this CO2 and CO feature in the NIRSpec range, and then again mainly water in the MIRI range. But there's also some stuff that doesn't seem to fit so well at the moment. So the question is, do we have this slope here? So this model cannot really fit for that. It looks fairly flat, but we have, of course, other data sets which kind of start here, which would indicate a slight slope. So it might also make sense to include them in retrievals as well. Then we have this dip feature, and I tried a lot of different parameterization of clouds to fit that better. But so far I haven't succeeded, unfortunately. Because when I looked in the literature, a similar dip was found in the case of WST39b, and in their models they used non-gray and inhomogeneous clouds, and they got like this dip to fit better. But no matter what I tried now in the retrieval setups that I used, it didn't seem to converge to a solution where it fits this apparent dip better. And then in the MIRI range, it looks a bit like it's dropping a bit lower here, and again, like our simple cloud setup is the one that prevents us from going to lower transit depth. So maybe that's another indication why a more complicated cloud setup would be needed to fit these data points that go a bit lower. But then again, if we look at different MIRI reductions, the two that we have currently, the other one goes a bit higher, right? So the noise is quite high in this range, and it's not entirely clear how trustworthy that data is or not. That was a bit faster than I thought. Then in terms of future work, so I will try more complicated retrieval setups, mainly more complicated cloud treatment. Then also non-constant TP profiles, non-constant abundances. So I've started some of that stuff. So far, not much improvements. And then it's interesting to see when we have the best possible metallicity and C/O ratio constraints that we have, what we can say about planet formation and population trends. But these, of course, are a bit tricky because we only get these metallicities and C/O ratios, which might be wrong because we aren't able to observe the entire atmosphere. We cannot see what's below the clouds. And then, of course, we also try to link them to bulk properties of the planet. But it might be that the behavior inside of the planet in the core is a lot different. So it's tricky to connect these things. That's still something that people are interested in, to connect it to disks and stuff like that, protoplanetary disks. Yeah. So just as a summary, I mentioned the many exciting new things we can do with JWST. And we have now a transit spectrum of FAP12b covering the entire accessible JWST wavelength range. The reduction can make a difference in the results that we can get, and that can also affect retrievals. And we can get a somewhat good fit, but there might still be remaining issues with the retrieval setup that we had, so that we probably have to try something a bit more complicated. Yeah.
Thank Thanks, Linus, for a wonderful talk. Now we have plenty of time for questions.
Hi, Linus. Thank you for your talk. I have an annoying question, because in your title you say you cover the full wavelength range, which is not true.
I included the word accessible.
Sorry?
Accessible. I included the word accessible for a reason, yeah.
Yeah, well, I mean, you can do transits with the MRS.
You can, yeah.
Do you think that adding more wavelength actually would help? Because you show that you improve your certainties on the fits and stuff if you have a wider wavelength coverage.
Yeah.
Do you think there's anything interesting in the longer wavelengths, or not really?
I have never really looked at MRS data, so I also don't know what kind of features you would see there necessarily. But what I know
I think
is
a lot of hydrocarbons.
a lot of hydrocarbons, yeah. But, okay, yeah, I'm not sure if there would be strong absorbers in a transmission spectrum. Yeah, okay. What I do know is that when people try to go for MRS data for these kind of planets, usually the signal to noise isn't that great, right? We can see already that we get these huge error bars if we are at the end of the LRS range, right? So if you want to go to even further to the MRS, where like the brightness of the star drops off even more, it becomes very difficult. So I guess you would probably need quite a lot of transits to get a good signal to noise, right? So I think just from that standpoint, it's difficult to do. And that's why, you know, I said accessible. But I've got that criticism before. The people said there's the MRS, of course, yeah. But I think it's just difficult to do for these type of planets.
Okay, thank you.
Hi, Linus. Thanks for the talk. I was wondering, when you mentioned the Rayleigh scattering by the clouds that you have at your shorter wavelength ranges, like, because your silicate clouds tended to cause these bumps at like 10 microns, something like that. But I was wondering, what kind of clouds are we talking about that cause the Rayleigh scattering part, like in terms of composition and maybe grain size?
That's a good question. So what you mainly characterize with the Rayleigh slope is I think, the size distribution of the cloud particles. I don't think it matters that much what the cloud particles are made out of. So that would be more something that you would try to figure out via modeling, right? That you try to figure out what kind of clouds could form, what kind of clouds would we expect there. So one simple way would be you look at the kind of temperature profile that you would expect, what kind of cloud species could condensate at the temperatures that we see, and then you would say it's likely one of these, right? But then figuring out if it's actually like one of these isn't trivial necessarily, I would say, right? Yeah. And you can also have like different cloud species and different kind of cloud layers, right? It doesn't necessarily mean that, you know, it can be a haze that is not the same as the thing that is producing your silicate cloud feature.
Yeah, because the main thing that surprised me is by how small the particles must be in that case. Must be pretty fine. All right, thanks.
Can you go to page 35?
Page 35.
Because I'm not so sure whether I understand fully this, those type of, what is in the y-axis and what is in the x-axis? VMR.
So the x-axis is the volume mixing ratio.
The what?
The volume mixing ratio.
Volume mixing ratio.
Yeah. So
yes. Which is?
Which measures how much of the atmosphere is made out of that specific molecule.
Volume mixing ratio.
Yeah.
Okay. So 10 to the minus 6 means that 10 to the minus 6 in mass or volume? No, it's volume.
It's a mass ratio, right? No? Number density, yeah. Okay.
Number density.
Yeah.
Okay, and in the y-axis?
Yeah, I didn't include an axis because it's basically it's a posterior, right? So it's like the density of that, like it's like a probability distribution of the kind of volume mixing ratios that we can have. So it basically tells you.
Okay, so the model says with this model I have the volume mixing whatever ratio has a certain distribution, and the points, so CH4 So the data tells you much less than the model gives in the green.
What do you mean the data tells less?
Well, if you look at the,
Yeah.
just try to understand the plot.
Yeah, sure. Yeah.
CH4.
Yeah.
So the data is what the crosses are, and so the colors, no?
No, there's no data here. So you mean these things?
Yes.
They're just so this is saying I think 95% of the you know, all the samples are left of that. That's what the errors indicate, or maybe it's sigma. I'm not sure. And this one is just the 1 sigma interval of the distribution. So these are
There
not
is no
data
data
points.
involved here.
The data is, you know, the data is basically this, right? So it creates, so it tries all these different kind of volume mixing ratios for the different
Yes.
molecules,
Yes.
and then it sees what kind of model it gets out of that, and then it tries
Yes.
to optimize how well that model fits to this data, right?
Yes.
And so we don't have data for this. This is like what we get from the sampling process. We get these posterior distributions from that. So these are basically the volume mixing ratio of CH4, SO2, H2S, that are all fit parameters that are used in the retrieval to fit the data.
Yes. I'm not so sure still whether I understand it, because the points, so you have the distribution
Yeah.
that I understand more or less, but
Yeah.
then the points,
these
but
are
take
basically
CO
just-
for instance. CO is easier because the errors are less. So the red point with the error bar, what does that contain as physical
So
information?
the point is the median value, and then
Yes.
these bars are basically the 1 sigma interval of the distribution.
Of the fit from that model to the data. Oh, it's a posterior distribution.
Yes, it's just
Ah,
it's
yeah.
just a summary. Yeah.
Okay. So
Yeah.
now, okay.
There's no data here.
Okay, still have to think, but
Yeah. Yeah. It's more because it's an upper detection limit, right? We can see that these, so this 10 to the minus 15 is basically the smallest value that we allow. And so likely what the retriever is actually figuring out is that there cannot be more CH4 than whatever 10 to the minus 6, but there can be less than that, right? Because it basically just means we don't have any evidence for a feature of CH4. Yeah. Where this point is basically, yeah. So it's to indicate, you know, it has to be less than that, right? Because we don't really say, we don't have like a mean value of where that should be. What the retrieval tells us is that it's less than that, mainly, yeah.
how well the fit is not.
I mean, the nested sampling, it optimizes for the best fits, right? So, yeah. I didn't.
2 slides back, you had like this staircase plot on the bottom left.
Which one do you mean?
Corner plots.
Ah, yeah. Wait a minute. Yeah. I think there's also one here. Yeah. So it's basically this, yeah.
All right, take it offline.
I have a shorter question.
Yeah.
Slide 42, I think that shows one of the spectra.
Yeah.
You mentioned the Rayleigh scattering slope,
Yeah.
but it doesn't seem like that's really fitted for.
No, it's not.
Oh, it's not. Okay.
Yeah.
Have you tried including that and seeing if that changes?
Yeah. But I also want to include that when I include maybe the STIS data or some of the ground-based data to go to the shorter wavelengths to see how well these match up. Because there isn't a lot of information here, and from the data that we had before, it looks like maybe it just kind of starts up here to go up. But then this is also the part where the NIRSpec spectra is the most noisy, right? So I'm not sure. I don't think there's much information just based from this data.
Okay, thank you.
So from what I saw, your spectra are taking at different epochs, right? So they're not simultaneously. So I was wondering.
The NIRSpec spectra are quite close. I think they're just a couple of weeks away, but
Okay.
the NIRSpec are a couple of months earlier. Yeah.
So I was wondering whether stellar activity influences your transmission spectra, and how do you deal with this, if it influences?
So we have. It's hard to see. So we actually do have at least like one. It's hard to see here. I don't have a plot for that here, but we have this slight deviation from the nice transit shape here, and that we attributed to a star spot, and we fitted for that. But this is like the strongest thing that we had. And then I compared the resulting transmission spectra, and the difference between them is really small. So it doesn't seem it's really a significant effect just when we treat it as a nuisance parameter, and we just are interested in the transmission spectrum.
But this is one observation, and now if you have observations weeks later,
yeah.
Is there a difference from stellar activity? This is what I was wondering.
I only worked on the data reduction of the NIRSpec data, but I think it's the only one where we saw like a deviation in the light curve that looked like something what a star spot might cause. I think in the other data sets there wasn't really any evidence of that.
Thanks.
But there have been, with other observations, I think people have detected like star spot features for IP12b, so it's it's a thing.
Despite long questions and answers, we still have plenty of time. So, who wants to ask a question? Honey?
Hi again. You said at the end that you were thinking of relating everything to the protoplanetary disk.
Yeah.
How do you plan to do this?
I have to look more into the literature, honestly, because it's very difficult. People do that, and then like there's always the same kind of obvious criticism, right? Like, is this really like an realistic estimates for like the bulk properties of the planet and stuff like that? So yeah, it will be a bit of a. I will have to look what people did before and try to discuss that in that context. But
Have you seen Paul Mollier's paper from 2022?
I'm sure I have at some point, yes.
Okay, because it will tell you that you can't.
Yeah.
At this point, at least, you can't really.
Yeah.
So that's just my warning, I think, before you go down that rabbit hole.
Yeah, I think it's probably should still be discussed, right? But yeah, you're right. It's tricky, but people are interested and want to do that, right? So.
Yeah, I think it's always the obligatory discussion section at the end of the. Anyway, okay. Well, good luck with that.
Thanks.
Maybe a pretty boring technical question, but just for, I don't know, my sanity and a point of comparison. How long does it take to run, for example, a nested sampling versus an MCMC walker for one of these retrievals? Like, is there one that's typically quicker than the other, or is it like, and what time scales are we looking at?
I think people use nested sampling because it's faster than most normal normal MCMC. Yeah. Because I like how I understand it works. You like narrow in on the center of your posterior distribution, right? You do that in like multiple nested sampling runs, right? So as far as I understand, it's like you do it because it's a bit quicker than standard MCMC.
Yeah. What time scales are we looking at if you run a retrieval?
For these retrievals, so I used like 64 cores for the fastest one, and then it could take for like if you include all the data sets like 3 days, 4 days. And that's a very simple, it's like basically the simplest retrieval setup that you have. Like every time you include an additional molecule, you include of course another parameter in your parameter space, and you can make it as big as you want. And then if you want to fit for a temperature profile, you say you have like 5 different pressure points with different temperatures. Of course you can make it as big as you want, and then quickly it can become unfeasible.
Yeah.
So there's also people that looked into machine learning approaches for atmospheric retrievals, because now that we have this better JWST data, we can also try to go for more complex models.
Yeah. Did you try different radiative transfer codes at some point, or did you stick to one general one and really eliminate that?
I mean, I guess implicitly I use different atmospheric retrieval codes that will have different radiative transfer implementations, right? But I didn't switch one out and kept everything else the same. No.
All right. Thanks.
So So we are breaking the pattern here a little bit, and I'm meeting Hans go to Thomas. We started with the pattern, so Danny, Ton, then you, and then Thomas, but now we are breaking the pattern.
Thank you. So it's about the next slide, my question. Slide 27, yeah. So here you rebin the full spectrum, but how do you choose the wavelength bin size? And does it matter a lot if you change a certain wavelength bin size? You do the fitting of the separate bins, and then you have a certain resolution, but then you probably also have to do a rebinning once you do the retrieval. Or do you leave the spectrum as it is?
I fitted them at the same resolution that I used also for the retrievals, right? But people have also, like also with this data, for the other data sets, people have tried full resolution spectra and stuff like that. Then of course you just have very noisy data points. And I think typically you don't benefit that much from that.
That makes sense. But is there a correct way to estimate the optimal wavelength bin size?
Not necessarily. I mean, you can, heuristically check like which one can you fit better, like where do you gain still information compared to other ones. But I think you kind of would have to try that out. Yeah. So I used a spectral resolution of 125, which a lot of other papers are doing. So I just followed that. So then some people in those cases have tried out full resolution spectra and said like this gives basically the same results.
Full resolution spectra also probably depends on the opacity data that is available to do these actual fits. And I don't know what's the resolution of these opacity tables.
I think it will be higher still.
For molecular bands as well? Okay.
I mean, I think, yeah.
Hi, thanks for the nice talk. My question is actually with the discussion you showed us with the different reduction pipelines that you have different results, and as well as the wavelength dependence, etc. Does this not also affect the retrievals then, depending on which reduction pipeline was chosen? Is there a consensus on which one is better or not? Or because as long as you have these differences, you will always, even if you include sophisticated information in your retrieval method, you would still have issues, right? As long as there is the differences in the reduction itself.
Yeah, that's also something that I'm investigating, like if that makes a difference. And we also did that already for the other papers, for the other data sets, where like we have like 2 reductions and we check how much do they differ. And in the case of the NIRSpec data, like one of them shows like there might be evidence for H2S and the other one says no, right? Then my hope was always like if you combine all the data sets, then like maybe kind of balance out. But I'm still trying to see that.
Okay. If I may ask just a small question, on your slide 8, so it was pretty much at the beginning of your presentation.
Slide 8, yeah.
Why is there this difference between the WFC and the NIRSS, ISIS, whatever, this offset in this data?
Yeah.
Why is there this offset? Is it supposed to be like this?
Like ideally you wouldn't have it, but we see these offsets quite often.
So it's just an instrumentation difference.
Like in the retrieval, I would fit for them typically, right? But they also have been worse. So especially the offset between the NIRSpec and MIRI data was quite bad at the beginning, and then like by tweaking the reductions and trying stuff, now they're much closer. So the offset doesn't seem to be so big anymore.
Thanks.
There is still time for questions.
Thank you, Linus. This is purely a curious question, but so you assume that the composition, like the atmosphere, all the features you see are coming from the atmosphere. What would be the impact if your planet had a ring, for example? What would you expect? Could you explain maybe the dip that you see in some part of the spectrum?
I mean, I've only heard people consider rings when it comes to just detection and having just the transit light curves of detection. Never thought about it in when it comes to transmission spectroscopy. I mean, I would expect it has to be much weaker, right? Because the ring is quite small, cannot absorb that much light. I think it would be like a effect that we wouldn't really be able to see. But then again, I haven't tested anything in that regard. Yeah.
It was just a curious question.
Yeah.
Okay, I see.
More questions?
I wrote down slide 36, and I hope I will remember my question.
Yes. Yes.
Yes, the right plot that fits the pressure level of the gray cloud deck seems strange that if you not include NIRISS, that you fit your cloud deck so poorly and so deeply, especially. Have you mentioned you have to look into that, or did you mention you have looked into that?
I don't think it was ever that extreme when I tried with previous reductions. So when I now reran this is what came out. So I didn't really have time to look much into that. But yeah, it's strange. Yeah.
I would be.
It's also different.
in
Like that retrieval is also different in many other properties, right? And that can be because it converges to a very different pressure level for the clouds, and that just makes a difference.
But if it's a true feature, it could be a cool discriminator between NIRISS and the other data sets.
Yeah.
Any more questions?
Thanks for the talk. So if I understood it correctly, there can be quite some time between observing the different spectra. So I was wondering, could like something like in the atmosphere of the planet change over that period of time, and could that like affect your fits, or do we not expect that?
Probably yes. But I think we're not at this stage yet where we would be able to model this and account for that. So there's a lot of implicit assumptions that we put into these kind of retrievals. But I know that for directly imaged things, where you look at these brown dwarf size objects, where you can study them in isolation, people have seen these changes over time and attributed that to variability. And I think even for some transmission spectroscopy stuff, people have seen changes. And then the question is, could this be some kind of variability, or is this just some problem with the data, or like how we reduce the data? So I think that's quite unclear at the moment.
Okay, thank you.
Any more questions? Lenny?
You mentioned that you do a 1D, so you assume one temperature for the whole atmosphere that you retrieve? Okay. I believe at some point I read a paper that said this was pre-JWST, that with JWST we would be able to trace temperature changes over the pressure that you trace with the transmission spectrum. Is this something that is true? I don't remember if this was actually the case. I think I remember reading this. Is this the case, and do you plan to do this?
Yeah, I've already run a retrieval like that, where it's just like 5 points at different pressures. But what I found out from that is that, like, for all the other stuff, it didn't really make a huge difference for the other molecular balances and stuff like that. So people are doing that, right? Yeah, it's a bit hard to say like how much can you trust it or not. Like, but then again, it's probably more realistic. Yeah. So it's definitely something that I will try. So there's plenty of room to add more complexity to fitting the data, and that's one of the things that you can.
Did you get certainties on the profile fit, or was it just you tried a couple and?
What do you mean? Yeah, did you get
posteriors? Yeah,
you get posteriors on the temperatures. Yes, yeah.
And these looked good, or was it super uncertain?
Yeah. I don't think I've analyzed that actually. Yeah, no. But I know from other retrievals that people have been running, they get kind of consistent results, and it looks somewhat realistic. But yeah.
Okay, thank you.
All right, I think it's time to stop here. Let's thank Linus again. And something that I don't do often, actually didn't do before, I would also like to thank you all guys. I want applause to this lovely audience because it's already the second or the third time that you guys feel like half an hour of time with questions. It tells me that you're guys interested in what's happening here, you're engaged, and I'm really happy to see all these discussions. So thank you guys. And happy holidays, and see you next calendar year.